First of all, thank you for the opportunity. The topic I would like to present has the title Towards a Measuring Tool for the Resource Effectiveness of Circular Economy Strategies, a Statistical Entropy Analysis. My name is Alexej Parchomenko. I'm a PhD researcher at VITO at the Sustainable Materials Management Unit and also at the TU Vienna at the Faculty of Civil Engineering with the research group Waste and Resource Management. And the pipeline is the Plastics to Resource. To give credit to my co-authors, I would like to point out their names, as you can see here. And if you need more information after this short kind of intermezzo presentation, you can also follow up these titles here. To start the presentation, I would like to point out one aspect, namely that our economy is mainly linear, which means we're highly dependent on resource extraction. And the recent report, the Circularity Gap report by the European Commission, shows that only 9% of the economy is circular. So we are far away from the circular economy, which requires quite some work and effort. And the question is, why is it that we are far away from the circular economy? First of all, the economic process has been described in many different ways. One of them that is relevant for the circular economy from our perspective is the following, namely that the economic process transforms valuable low entropy materials into high entropy waste and emissions. What is meant by that? If you look on the input side of the production processes, we usually have quite pure material inputs that are combined in a very specific way to produce products for the end users. But after some lifetime, these products become waste, which means that the entropy of that fraction is higher than the input fraction. And the circular economy, also, of course, the emissions that happen all along the value chain further increase entropy in the system. And the circular economy exactly wants to reduce this entropy increase by the preservation of functionality of these products and materials as long as possible, and also the value of these materials and products for as long as possible by different strategies, and also by recycling of the waste fractions back, and by the restoration of the functionality on the product, on the material level. Statistical entropy exactly uses this kind of characteristics, namely it is a method that measures the distribution of a set of characteristics, which makes it a very generic method, which means that it can be applied to substances, different plastic types, brand of EV batteries, etc. To show you a little example how the method functions, I would like to use colors of different plastic pellets. These could be also different plastics. So if we have a bowl of plastics with a single type of plastic color, the statistical entropy value of that fraction is 0. We have the full information, we have a perfect concentration of this single type plastic. And if we start mixing or increasing the diversity, the dilution of different plastic sorts in this fraction, we see that the entropy increases in our system. And this is a very relevant property for the circular economy assessment. It has been recognized in early, before the circular economy concept was that popular, and it has been applied to copper. This is just an example of how the method works on a single substance level. So similarly, if we have the ores that we concentrate to a pure metal, statistical entropy decreases. And usually this pure copper is integrated in a certain type of a product or a subassembly, which increases statistical entropy again. Now, when these cables become waste, for example, statistical entropy increases further because these are mixed with other fractions, for example. And we already see the problem here that all the reductions or changes in statistical entropy, also the increases, require certain effort which is measured as the distance to the ideal state, in this case the functional product, let's say, and we do it in terms of the changes of statistical entropy. So defining a resource-effective system, we look at the circularity baseline and say that the resource-effective system preserves functionality on the highest level possible. In this case, it will be these cables with minimal effort. So the functionality is not lost over as long as possible over the time of the product lifetime. And this concept we use to analyze different systems. And especially we extended the method from a single substance application, as the circular economy has other further strategies such as the repair or remanufacturing strategies, the waste collection, etc. So we can analyze different circular economy strategies and their combinations only if we can assess not only a single substance in a system, but their combinations, so that we can also express products and component statistical entropy values. And I would like to provide a short, very basic example of which we calculated to prove the concept of the method, namely this very simplified car with a very simplified system of production, disassembly, shredding, and extraction or recycling. And we use different scenarios with different recycling efficiencies that produce these curves over here. And we can already see that high recycling reduces statistical entropy to a higher amount in the end-of-life recycling activity than lower efficiency. And we also see a second effect, that if we reuse or maintain the functionality on the component level, the increase is lower in the shredding stage, which is quite logic, but this shows how the concept works. So we can also run the system over several cycles. So let's say 4 cycles, and we can see the performance, the black dotted line of the linear system, that each time we need the full input of resources, and in the end of that life cycle, they all become waste. In relation to that, we can see the highly value maintaining or functionality maintaining system, where all components are constantly reused, there's no waste, and all the other systems are in between. What is important is that not only the performance in the end of this simulation, but also the changes of statistical entropy, as we said already, that these are related to some kind of efforts, some type of efforts in forms of energy or manual labor, etc. So applying this concept to a more complex study, the electrification of the European vehicle stock, we used some scenarios with also different recycling and reuse of components, but also lifetime increase of the vehicles. For that, we also need the vehicle model, which is shown here. We have a normal or still normal internal combustion engine vehicle and an electric vehicle, for which we can already calculate statistical entropy values on the component levels. And we run the system for several years for the entire stock of cars, for the production system, the use system, and the end-of-life treatment system, with very typical processes of dismantling, hammer mill separation, magnetic separation, etc. So these are kind of end-of-pipe processes applied, but we also have reuse of components. What we can then model is for the internal combustion engine vehicles and an electric vehicle, we can model the statistical entropy changes for a life cycle of each single vehicle, for example, or for the entire stock. We can aggregate those statistical entropy values for each car over its life cycle, or we can aggregate it for an entire stock of vehicles, which we can see here. And now I'm aware that you don't know the exact scenarios, but yeah, the reuse scenario implementation. It's recycling means that we increase the recycling efficiency, and what we can see is basically shifts in the curves. For example, if you make a transition towards electric vehicles to 100% until 2050, so rapid transition, we get this red curve. If we reduce the speed of transition, we delay the transition, but okay, it means for that specific year we reduce the effort performed in the system. If we implement reuse and recycling strategies, we can further decrease the effort needed in the system. Also the demand reduction, which means that there's ride sharing or car sharing services implemented, can lead to reduced statistical entropy values, also the lifetime increase. So it shows that some effects are immediate, others are long-term, and this is a way how we can analyze statistical circular economy transitions for any type of system that can be mapped in the terms of a material flow system. So the conclusion and collaboration possibility results from that first of all, we would like to stress that it is maybe important to find effective systems first. So this is a perspective that doesn't look at the background system, which means that in the second step we should optimize the system that is effective for efficiency. It means that what the method can be a strength and a weakness of the method, namely that it is independent of the background system. So we don't really care how the effort is delivered. It can be based on different energy mix of the system. It can be performed by manual labor or automated processes. It is not considered in the system, which means that we first analyze it independently of the background system. And from this novel perspective results in our view, which gives us plenty of opportunities. Also, due to the generic concept, we can apply it to different case studies for plastics recycling, which you will hear in the next session, I think, and we can also link it in the future to the efforts required actually and the environmental impacts, and extending it also to other hierarchical levels. So we can go to the regional level, or we can go, for example, to the monomers and polymers if we would like to analyze those. The only thing we need really is sort of a material flow system with the compositions of each flow. And with that, I would like to thank you for your attention, and I'm looking forward to the questions.